So we stay with Salomon with a more specific example about downhill trace. So the only thing I've learned is that running uphill, everybody knows how to do it, but downhill seems to be something that you're going to explain us.
Morning, everyone. I'm Sébastien. Like Nico and Lise, I work for Salomon and more generally for AMA Sports, the AMA Sports group. Actually, Nico is my boss, so I'm going to try to do a nice presentation. Like Nico said, trail running is quite different from road running, and it's quite different from running in the Bois de Boulogne, for example, because you have uphill and downhill sections. And so like we said, the uphill is quite well documented. And what here we wanted to try to do was understand the downhill performance and model that not from a finite element perspective, but from a multiple factor perspective. So that's it. What we wanted to do was determine some key factors that influence the downhill performance. So here at the center we have the downhill performance. It's basically the time that we measure on a specific downhill sections close to our office. I'll show you after that. And we tried to explain these performance by several parameters, and you have them all around. So first, proprioception, the foot strike pattern that Nico gave a word about. We had the psychological state, the motivation, basically. Some muscular abilities, some visual perception, and as well the maximal aerobic speed. So we had a very large, broad variety of parameters to explain this downhill performance. And what I'm going to do is focus on some of them and show you how we used a bit of mathematics, pretty simple mathematics. Nico said more complex, but you'll see that it's pretty simple mathematics to explain the downhill performance. Just to show you, this is pretty close from our office. So it was just to make you a little bit jealous, you know. This is where we live, basically, and this is where we measured the downhill performance, because the downhill was just here, where it's alighted. And it's real. We did experiment the downhill performance on this place. Okay. First parameter that I wanted to focus on is the foot strike pattern. So I'm gonna be pretty quick because Nico gave a word about that. Basically, in this parameter, we want to know if the runner is striking the ground, is touching down the ground with the forefoot first, or with the rear foot, the heel first. And it's illustrated here. For example, these first images are taken with the forefoot striker runner. There is a nice animation after that. So you see here, the touchdown position is with the toes, the forefoot first. And in the other one, you have nice rear foot strikes. So touchdown position with the heel first. And you'll see after there is the stop on the video. Here, you see heel first. How do we do that? We put two accelerometers. I think I have a laser over there. Yeah. We put two accelerometers on the shoe, one at the metatarsal level, one on the heel. We have these nice graphs like Nico showed, and we just calculate the time difference between the peak observed on the forefoot, on the accelerometer on the forefoot, and the one on the heel. So it's pretty basic mathematics, just a subtraction, and we have this nice parameter just to see if the runners are running forefoot or rear foot. Second example I wanted to focus on is the proprioception. So basically here, what we want to do is see if the different runners use differently the information given by the ankles, the proprioceptive information given by the ankles. Basically, proprioception is the information used by the system to locate in the environment. It's used for motor control, and the hypothesis was maybe faster running downhill would use a little bit more the ankle information to control those movements. How do we do that? We put the runners on a force platform over there. Basically, there is here a schematic representation of what is a force platform. And the important thing is that we get from this force platform 6 parameters. So the forces in the 3 dimensions and the moment around those 3 axes. And what we want to do with these parameters of the force platform is calculate the center of pressure coordinates. So basically it's the projection of the center of gravity, it's the barycenter of all pressures. And it's even during a standing trial like that, so here is a standing trial, the task is pretty simple. We ask the runners to stand still, eyes closed, and we measure the trajectory, the path of this center of pressure. How do we do that? Pretty simple mathematics. We want to calculate the x direction center of pressure and y dimension. We just have to divide a moment by the vertical force, and we have the coordinates. And after that, we have some graphs like that. After that, well, on top of that, we have a specific procedure to ask the system if the ankle information are used or not. So during the standing trials, the simple task that we talked about, we have some vibration. The red circle here highlights some vibrators that are put onto the muscles. And basically this vibration is going to induce a perturbation in the system. And this perturbation is, can be seen here on the center of pressure signals. And what we do basically is analyzing these perturbations to calculate what we call a relative proprioceptive weighting by this equation. And that illustrates the weight of the ankle proprioceptive information. So basically it tells if I use very much the information coming from my ankles or not. And we can put, so for example, for this example, we can do the calculation and we have an 89% relative proprioceptive weighting, meaning that this particular runner is using very much its ankle information to control his standing posture. Pretty simple mathematics as well to calculate those parameters. Third example I wanted to show you, it's the muscular abilities. And here what we wanted to do is calculate a power during a vertical jump. So here it's no big news that the power equals force times velocity. And what we asked the runners to do here was to jump on a force platform over there and jump as high as possible. And since we asked them to jump on the force plate, on the force platform, we had basically the ground reaction force. So we had the first parameter of the power, that is the force. Okay, but how did we calculate the velocity? And here we remembered this good old Isaac Newton and his second law to calculate the velocity, because if we take a look at what forces are on the play here during a vertical jump, if we take a look only at the vertical dimension, we have the weight that equals the mass times the gravity vector. And we also have the lower limb force that is given by our force plate. It's basically the ground reaction force in the vertical dimension, in the z dimension. And then we use the equations of Isaac Newton to manipulate those parameters and to have, at the end, the acceleration of the center of mass. And by simple integration of this vertical acceleration, we can have the velocity. It's a pretty simple mathematical method as well, because this integration is made by an analytical method and not a computational method, so it's pretty easy as well. Okay, for that. And last but not least, the overall example is basically we wanted to explain the downhill performance by all these parameters all around. We wanted to see the strength of the association between all these parameters and the downhill performance. And here is the more complex method that we use maybe. So basically we wanted to build this predictive model of the downhill performance. So to get this kind of equation, for example, we wanted to see, okay, the downhill time equals this kind of ponderated equation. And for that, we use a method that I think is called the least square method. And so we we basically solved some equations. And I said we, but we had help because we used some specific software to do that. Basically, these kind of equations are like a black box for us. We know the principles, but we surely know the philosophy of them, what they allow us to do, and we know in which software we can do that and have the proper result. Okay, just to give you the study results, how the performance, the downhill performance is explained. Here's the equation, basically, that we can get. I'm going to explain a little bit with some images. It's going to be easier. So the downhill performance is explained by the foot strike pattern for 25% of the contribution. That means that if you land on the forefoot during the downhill, you're more likely to be faster. We had the visual reactivity. It's one of the other tests that we took. If you're pretty fast in reacting to some visual stimuli, you're more likely to be fast during the downhill. We had 17% contribution for the quadriceps, so the thigh muscles explosivity. So if you're able to develop a high force in a low amount of time, you're more likely to be fast. And last, the ability to take risks. So it's more of a psychological parameter. If you have no brain, basically you go faster downhill. And as usual, we have an unexplained part left, 21%. And basically that are the contributions that are computed from this equation on the top of that. I have a few take-home messages, if I may. First one is that during this study, we used some simple law of physics to describe the human movement. So you saw that we used the Isaac-Newton equations. We used some even simpler mathematical tools to compute our relevant parameters. And we had the help of dedicated software to perform the more complex analysis. So, like Nico said, we're a bit stupid as biomechanists, but we can have some nice results by using the nice and the relevant tools for those kind of studies. I want to thank you, and just before you ask, yes, that's me on the right. Thank you for attention.
Time for questions.
So, thank you for this very nice talk. I wanted to know, you proposed some linear regression model, and did you try to do some more complex statistics, adding more variables so that maybe you can explain the 20% that are still unexplained?
Actually not. We used the multiple linear regression because it was the simplest for us, and that was in line with our hypothesis. But we had already plenty of parameters. I think it was like 25 or something like that that could explain the downhill performance. But yeah, there is still 21% left, and we could run some more tests to try to explain this black part.
Yes, my own experience in trail running is the fact that the experience is critical to run downhill. Maybe that explains a bit the 21 missing %, or?
It could, actually. We recorded the trail running experience, and I can't remember actually if we included that in the model, but I'm pretty sure we did. And but we had some experienced runners basically in that study. We had 28 runners, and they all practiced trail running for at least 4 or 5 years, so they were pretty much experienced. But that's a nice one. I think we could have some more differences between non-experienced runner and a group of more skilled trail runners, I guess.
I have 2 questions. One is about, you start from very simple law of physics, which I think is very good, and I don't understand why you don't push a little forward in these law of physics. Because, for instance, when you jump from one foot to the other, you have gravity for the whole duration of the jump. But of course, the impulsive force, or what you call your limb force, doesn't stay for the whole jump. It just pushes you. And there are models, I have seen models where you can, write Newton's equation, taking care into the gravity and this ratio between the time when you push and the time when you're in the air, in some sense. So I think there are ways to write the equation, to go into the next step, that is not stay, at the kids level, but move a little higher in Nico's picture, and try to explore these lower physics a little bit further. Have you tried this, or?
Actually not. My only question would be, why would we do that? What kind of parameters, what kind of explanations would we get from that? And if we haven't done that, basically is that on the one hand is that we don't really master all those tools, and on the other hand is that, okay, what kind of new parameters, what kind of new explanations of the movement would it get for us? And that's the part in which we are the lowest skilled, I guess. So we need, I think we would need some help to understand what can it bring to those kind of studies.
I think, my hope would be that it would reduce the number of parameters you put in your very big equation, statistical equation. If you have a stronger model coming from the law of physics, then you reduce the need for statistic because you're able to predict better. So that would be my hope.
Sure, I would be happy to collaborate with you if you'd want to do something like that.
Any other questions?
I have two questions. First of all, are the shoes that you have today downhill shoes?
Actually, all our trail running shoes could be used for downhill, but this is another project. I can give you a word after that if you want. It's a brand new project for customized shoe, but that's another story.
And so my second question is quite related to the shoes. In the first talk, your colleagues were explaining that in tennis you may have to glide to gain something. So when you do downhill running, probably that you have to glide from time to time. So are the shoes, can the shoes be thought similarly? And how do you take that in the model to build them?
For the gliding, sliding part, I'm not really comfortable with this because I think the higher the grip we have in the downhill or the trail running sections, the better it is. So I don't really know, but if you have a look here, maybe just, oh, sorry about that, with our parameters. So here, if we take all our influential parameters, the one that can be influenced by the shoe is basically this one, the foot strike pattern over here. Because like Nico said, we know that when you lower the drop, lower the stack height, so the thickness of the midsole, the global thickness, you're more likely to forefoot strike. So basically you could improve your downhill ability by choosing a shoe that has a low drop, low stack height.
Okay, thank you.
Thank you very much.